Okay, so in this video, we are going to talk about the relationship of force applied to the force of friction. So I have a diagram here for us to get started. We have force applied on our x-axis, force of friction on our y-axis. And there's some key things that we need to see. So to start, we both start at zero. So if you have no force applied, then you have no force of friction. Hold on, I do need to go back and start and talk about that we are talking about an object that is at rest, or at least that starts at rest. So an object that starts at rest. If an object is just sitting on the ground, there is no force applied, then there is no friction. As soon as we start to apply some force, you can see that we actually start to get some force of friction. Now, for this entire diagonal part, this is actually the line y equals x, which means that your force applied is equal to your force of friction. So until you hit this point here, until you hit your force of static max, your force applied is your force of friction. Once again, until you hit your static mass, your force of friction, static max, your force applied is your force of friction. You can also come here and say force applied equals the force of friction, which is the static one. So that's a little cursive S there for you. What this diagram then shows is that eventually we hit this maximum point. When we hit this maximum point, it's known as overcoming static friction. So in order for us to actually put the object in motion, which is this category here, we have to get a force applied that actually goes up this high. Our force applied has to reach that maximum point. So once again, the force applied must reach that maximum point. Otherwise, it's always going to be at rest. We can't move into the kinetic zone. You have probably seen that the force of static max is equal to mu s force normal. So the force of static max is equal to mu s force normal. You will often see force of static is less than or equal to mu s normal. So use it in for normal as in also for force normal, the same thing there. That is because that is what this point here is. This point is actually mu s force normal. So this entire time up until then, our force of static friction is actually less than that. So our force of static friction is the force applied if we're not in motion and we've not hit this maximum. As soon as our force applied gets even on the easiest other side of this maximum, our object starts moving and we're in the kinetic zone. So once our force applied surpasses this point, whatever this value is, then we can go ahead, our object is now moving and we have kinetic force. Force of friction kinetic is equal to mu kinetic force normal. So we do have that relationship of mu and force normal. But for static, we can only say that when that is the maximum. If it is less than the maximum, then we're not in motion, we're still at rest. So the demonstration that I do each year, because we're not doing it in class, I'm going to try and show it to you guys using some pictures. So those of you who've been in my classroom before have seen my lovely shed, and you know how heavy it is. So here I am trying to move my shed. So I'm going to create a free body diagram. There are four forces. Let's say four forces here. There is my force applied. There is the force of friction. And here I'm going to go ahead and put S because my shed at this point is still standing still, so we're doing static. I have my force normal and my force of gravity. Now, it is hard to see because this is obviously a still picture, but I promise you this shed is not moving with me only putting one hand on it. The shed is much heavier than that, so we're going to say that the shed is at rest. So therefore, I can do my sum of forces. As always, go ahead and label your positives and your negatives. So I'm going to say the force of static, because that's in the positive direction, minus the force applied, because that is in the negative direction, is equal to 0. And I can do that because it's at rest. Therefore, we're saying the force static equals the force applied. So my frictional force here is simply the force applied, and that's because I was not able to overcome the static friction. How do I know I wasn't able to overcome the static friction? Because the shed had not moved. It was still sitting there. So obviously, pushing with one hand wasn't quite enough. So I said, well, what about pushing it with two hands? So let's draw another free body diagram. I'm going to make my FA bigger because I'm really pushing with two arms, so I'm pushing with more force here. I'm going to still have my force of static friction. I still have my force normal and my force of gravity. Now, unfortunately, this shed is so heavy, and today was leg day, not arm day, so I'm not that strong, and guess what? It was still at rest. So even though I was pushing with both of my arms, I could not move it. The force of friction, of static friction, was too strong. That maximum value was too strong. I could not overcome it. So once again, when I do my forces in the x direction, this time I'm really going to mess with your brain. I'm going to make positive in the other direction, and I'm only doing that because I'm trying to move in that direction. I want my velocity and I want my acceleration to be in that direction. They're not currently, but I want them to be once I start moving, so I'm going to make that the positive direction. So that would say that the force applied minus the force of static friction is still, you know what, equal to 0 because it's not moving. So once again, though, I get force applied equals the force of static friction. Now, it's really important to note that this force applied, so let's call it 2, and let's call this one 1, because one arm versus two arm. So if we were to compare these, if I had FA1 to FA2, well, the second one is larger because I was pushing with more force. I had both arms going, it was more force. That means that the force of static 1 if we were to compare the force of friction in both of these cases, it would be larger in the second scenario because it is equal to what I am pushing. It is equal to that force applied. And that's because we know that it's at rest. So when I set equal to m equals a, we don't have any acceleration. So therefore, this is equal to 0. So they must equal each other. But the force of static in my first situation with one arm is once again less than the friction here. So it's equivalent to how hard are you pushing. So I couldn't push with both arms. So I got a little courageous here and I turned around and said, can I push it this way? So what happened at this moment, and maybe you can notice via the ground, my thing was actually right here next to the red poster. Notice that I was right next to that red snowflake. Well, now my red snowflake is over here. That means, guess what? The shed finally moved. So I'm going to kind of do this in two different steps. I'm going to do it at the moment it starts moving. So the moment it starts moving, or right before the moment it starts moving, I still have those same forces. I'm going to go ahead and make my FA even bigger. Oh, I should change colors. We're doing a new situation now. So I'm going to make that FA really big because I'm pushing with everything that I have now. Now, once again, you might be going, why are you still using static if it's moving? I'm saying the moment it starts moving, or even the moment right before, So when I hit that threshold, when we hit that threshold, we now say, same thing, doing my sum of forces. I'm still going to say it's 0, but because I know I'm about to start moving, it's that moment before, I know that what I've hit is my Fs max. So now I would actually say Fa is equal to Fs max. So Fa is equal to mu s force normal. This is the first time I actually finally got to this force normal situation, so I would need to deal with the sum of forces in the y direction. In the y direction, I would have force normal minus force of gravity equals 0 because it's not moving in the y direction. It's only moving left to right. And then, because of that, we say force normal equals mg. So I can come down here and say that at this moment, my force applied is equal to the force of static friction max, which is equal to mu s mg. So whatever is the mu of the shed between the shed and the floor, that times the weight of the shed and gravity, or sorry, the mass of the shed and gravity, so just the weight of the shed, is equal to both the force, the maximum force static, and my applied force. That is how much force I had to put into this to finally make it move. But something really interesting happens after that. I'm going to make fun of myself here. You can see my face kind of moves. I'm into the excited, oh my God, it's moving, into the relief stage. That is because once you actually start moving it, it kind of gets easier. So now, we're going to do that free body diagram again. But this time, I'm going to note that I actually have acceleration in the left x direction. That is just in the x direction. It's not my best drawing. So I still have force normal, mg, my force applied, and because it is moving now, we actually have force of friction kinetic. The mu k is always smaller than mu s, so therefore mu k normal is less than mu s normal. So now I'm going to say my force applied didn't change, but I have acceleration in this direction. So when I actually come in and do my sum of forces this time, I'm going to do force applied minus, oops, that's a minus sign, the force of friction, but I can no longer set it equal to 0. For once, I'm finally going to set it equal to max. So I don't know what my force applied is here. I could say if I was being consistent, that is exactly what I did up here in order to surpass, but I'm not positive. I may have actually pushed a little bit harder than that maximum. But here we now have this situation, and we would say that force applied minus the force of friction, because it is moving, is now kinetic. So mu k mg, I did that mg because once again these two are equal, is equal to max. And this is where oftentimes you might be given some information about the acceleration and you can solve backwards. And once you get moving, oftentimes once you set it in motion, this disappears really quickly, and you'll just talk about how the force of kinetic is the only force there, and the acceleration would cause it to stop moving. Here, though, I am still trying to move it. I am still giving a force applied, so simply that friction is just causing it to be harder to move. But because of this situation right here, that your kinetic is smaller than your maximum static, once it becomes in motion, it actually becomes easier to move. It is harder. So I guess end goal there, it is harder or more difficult, or even requires more force to set an object in motion, so something that's starting from rest and putting it into motion, than to keep moving. So you have to, if we think back to that diagram we saw at the beginning, I have to get a higher force applied. I have to give a higher force applied here in order to actually set it in motion. And then once I set it in motion, the force of friction drops. It becomes lower, so I'm opposing less. So most problems when we deal with, and in my next video, I'm going to do some problems. We actually have to figure out, have you overcome this? So if you ever start at rest, the first thing you have to do is find out, is the force that is being applied, is it enough to overcome that maximum static? If it is, then you can say it's in motion and we're dealing with kinetic. If it's not, then that force static is actually equal to the force applied. So I'd even say 9 times out of 10, if the question is asking for force of static, it's actually just asking for force applied. That 10th time is when you actually hit that force of static max, and the force of static max we said is mu s force normal. And you find your force normal from your sum of forces in the y direction. This is a big thing too while I have your attention. Do not make the assumption, that's a key there, that Fn equals mg always. Fn equals mg when a in the y direction equals 0 and they are the only two forces in the y direction. Otherwise, that is not the case. So make sure that you are always fully calculating what your force normal is. So just to show you again really quickly, at the very beginning with one arm, small force applied, small force of static friction. A larger force applied gave me a larger force of static friction, but I still wasn't at that max. As I put even more force in, I finally got it moving, so it meant that at some point my force applied was larger than that maximum. So at some point my force applied was actually larger than that maximum. After I hit that very special, that critical moment, then it was kinetic, and from there on out, my diagram looked like this, and I was only dealing with force kinetic. So once it's in motion, you have force kinetic, but you cannot get to force kinetic until you've done this critical point of overcoming that maximum static friction.